Okay, we're going to look at what is called the translational look-aside buffer now. So this is in continuation with paging, basic paging, which we saw in the previous segment. So in paging, if you remember, okay, I will go to that page, one second. So we looked at this diagram to understand paging, right? And what happens here is you take this logical address, you take this logical address, you compare it one by one with the entries of the page table until you find a match. Then you see the corresponding frame number and you use the offset, whatever. So the thing is, this comparison, it happens sequentially. And I guess most of you will have done your data structures course by now. So when I say sequential comparison, you know it is going to be order of n. And if your page table is very long, which is possible because I said 64 GB, I'm dividing it into 32-bit sizes, right? So that means there are going to be a lot of pages, which means this table is going to be very long. So a sequential one by one order of n comparison is going to cost us a lot of time. So obviously the next question as computer science people which we are going to ask is, can we do better? And the answer to that is the translational look-aside buffer, which is what we're going to see right now. Okay, so that is the motivation behind coming up with this entity called the translational look-aside buffer, which we call the TLB. So if you see here, with the basic paging scheme which we were looking at, you need two memory accesses to access your data. So first you have to go to the page table and you have to find the page number. From there you find the frame number, you go to the main memory and then you access the frame number. So there are two things happening, and that means memory access is slowed by a factor of 2. Also, the first check in your page table is going to be a sequential one. So once you get the frame number, you can probably jump directly to that frame in your main memory, in your physical memory. But to get the frame number, you're checking the page number one by one. That has to be a sequential thing, right? So that is a delay and a costly delay. So the solution for that is to use a small fast lookup hardware cache called a translational look-aside buffer. So the name itself suggests that this is a cache memory kind of a thing, which means it is going to store page number, frame number data for some specific pages, the ones which are most frequently used or most recently used and so on. Again, which page number, frame numbers go into the TLB? There are multiple algorithms which are very similar to your cache replacement algorithms. You have MRU, LRU, most frequently used, least frequently used. You have all of this, right, which you would have come across in computer organization. Similarly, so whichever pages I access most recently, that can be in my TLB. Whichever I access most frequently, that can be in my TLB. Whatever, again, there are multiple such choices, and the actual implementation varies with architecture. So we will not go into that aspect of things, but the idea is TLB is cache for your page table. So just as you have a cache memory for your RAM, you have a small cache kind of thing for your page table, and that is called the TLB. So it has what we call a key and a value, which is basically your page number and frame number. I'll move directly to the image and explain. Let me zoom out a bit. Yeah. So what happens is, see, again you have the CPU, you still have the logical address still has the page number and offset, right? So far so good. Now first what we do is, we take the page number and we check it in the TLB. Now the same thing, look at it as the main memory cache memory analogy. When you want to access something in the main memory, you first go check if it is there in the cache, correct? That is what we are doing here. TLB is simply cache for the page table. So first check the page number in the cache memory, and the thing here is, in the TLB you don't have to check sequentially one by one. You can check with every key or every page number parallelly. So all these checks will happen in parallel. That is because the TLB is a piece of hardware which is designed in such a manner. So we're not going to go into the intricacies of its hardware and specifications, but for now just know that TLB is a piece of hardware designed in such a way that it has key value, or in this context page number, frame number, And when you're doing a search, you don't have to do a linear search, you can do a parallel search. If I give page number is 5, each of these will run is page number equal to 5, check concurrently. So if that page number happens to be in your TLB, there will be a hit that will give you the frame number. Offset, as usual, you take directly from your logical address, you combine that and go to your physical memory. Supposing it is a TLB miss, in that case you will go to your page table, check sequentially, find the frame number, go here and continue. So it's the same thing as your main memory, cache memory. You check first in your cache memory. If it's a hit, you go directly access. If not, you go to your main memory. Same logic is happening here. You check in your TLB first. If it's a hit, well and good, you get the address, you go directly access your data. If it's a miss, then you come to your page table and access, right? So that's the idea. TLB of course is not as big as the page table. Your cache is generally smaller, right? So TLB is also smaller. The only extra point you need to know here is that TLB is designed to support concurrent or parallel search operations. So it saves time. So that is how your TLB is saving time. 1, because it is smaller in size, of course, and 2, because it supports these parallel search operations. Right, so a little bit of math related to the TLB. One thing we need to know is the hit ratio, which is the percentage of time the page number of interest is found in the TLB. So let's say I'm looking for 10 different pages in the TLB and 8 times I found them here. 8 times there are TLB hits and 2 times there are misses. Then it means 8 by 10, which is an 80% hit ratio. Simple, straightforward stuff. Second, effective memory access time is how much time it takes effectively to convert the logical address to physical address and go access the memory. So this you have 2 cases, right? Either you find the thing over here itself in your TLB itself, or it is a miss, so you have to go and check your page table. So these are the 2 scenarios. So the effective memory access time is hit rate into time taken for reaching from the TLB to your main memory, plus the other condition is miss rate into time taken if you want to search your actual page table and then go read. So effective memory access time basically is how much time you need from the time your logical address is generated to the time your physical address is generated, right? So how much time is needed to translate the logical address to the physical address. So first case, it is a TLB hit. In that case, how much time you need is the hit rate, which is probability of getting a hit, into the time taken for searching the TLB and getting the answer. Second case, it's a TLB miss. So what happens is probability of getting a miss, which is miss rate, which is 1 minus hit rate, into time taken for searching your actual page table and getting the answer. So this probability into time, this probability into time, and because it is 2 alternatives out of which any one can happen, we add up. So that is the effective access time, memory access time.